Okay, I think we're recording now.
Hi, Manette.
Hi, Manette.
Hi, Manette.
We're going to try to do this lesson for you on paper, and hopefully it'll work out great. So what I was telling our friends here, and you too, but you're sick, is that we have lots of work to do. This is what we have left to do for the rest of the year, and it's quite a lot. And we have 14 class periods basically before I want to start reviewing, and so we need to be moving along quickly. And most of the work we're going to do is right out of our review books. So we've already done some integrals, and we're just going to continue on doing that sort of stuff. Integrals. Okay. So today, oh yes. So you're writing, Manette.
Here, wait. It's different in ours.
It's a different page, but it's the same stuff. So we have here, Manette, these formulas that I'd like you to put into your notes right there. Hopefully you can see them. I don't know how.
Page 147.
Okay, page 147. It's page 151 in my book, or 147 in your book. And we're going to look at these just briefly, and then we're going to do a couple problems with them, and then we're going to move on. We're just using these formulas. So you'll notice that there is a constant multiplier for the variable, and that constant multiplier is just going to end up as the denominator in each one of these cases here. Not okay?
No, I'm fine. It's just going to be very confusing on video.
Okay, well, that's the way it is. Well, that's what you get for being absent. Okay, and so we remember that the integral is the opposite of a derivative. So I want to take a look at this formula right here. The integral of cosine of ax equals sine of ax over a plus c. So I actually want to do a problem with that formula. So we're going to do, let's do the derivative, d dx, of sine of 3x over 3 plus 5. So we're doing the derivative of that to show that, to verify the relationship between the integral and the derivative. So if we want to do the derivative of this thing right here, how do we start?
Take this 3 and make it 1/3.
So this 3 right here?
Yeah.
And make it a 1/3. Okay, so that's fine. So we have d dx of 1/3 of sine of 3x plus 5. Still good. Now what do we do?
Derivative?
Derivative of what piece is really the only piece that we need to worry about?
Sine x.
The sine of 3x is the only piece we need to worry about.
Yeah.
Right? Because the 1/3 is a constant multiplier. Don't need to worry about that. Doing the sine of 3x, which we'll do in a minute, the derivative of 5 is obviously just 0, so we don't need to worry about that either. Okay, so let's go ahead and do this. So how do we do the derivative of the sine of 3x?
Cosine is 3x.
Good. So the derivative of sine is cosine. And this is a function inside here, so we really have to think about the chain rule. So this is going to be equal to 1/3, right? We just bring down the constant multiplier. The derivative of sine is cosine of 3x. But since this is a chain rule, we have to multiply this by 3 because that's the derivative of the inside function, so times 3. And then the derivative of 5, of course, is 0, so we don't even write that. And then we have 1/3 of the cosine of 3x times 3. 1/3 times 3 makes 1, so we end up with just cosine of 3x. So we remember that the derivative and the integral are opposites of each other, right? So back to our formula here. So actually, let me just write this one bit right here. So the derivative of this is this. Therefore, the integral of this is that. Right? Derivative goes one way, integral goes the other way. So we just took the derivative of this thing right here. Taking the derivative of this gives us this. If we work backwards, aka do the integral, and we do the integral of this, we should get that. Does that make sense? Okay. So the integral of the cosine of 3x dx, we always have to write the dx, equals what we have up here. Sine of 3x over 3 plus 5. that, I was getting nervous when that happens. If we compare that to our integral formula right here that we just looked at, the integral of cosine of ax, which is what we just did here, the cosine of 3x, equals the sine of ax, the sine of 3x, over a, over 3. We have plus 5, they have plus c, just some constant. So all we did is we just verified this rule right here. That's all we did. It's okay? All right, great. So you'll notice then as we look at these, I want you to think about the question always. As we look particularly here at this one, I like. The integral always asks, what is that the derivative of? So if you remember back a little bit and you ask yourself, secant squared, what is that the derivative of? That's the derivative of tangent. And there it is, tangent. So you always have to ask yourself, when you're looking at an integral, what is that the derivative of? And that will help you to be going in the right direction.
So that'd be negative cosecant, the derivative of negative cosecant.
Where are you at?
I'm looking at the fifth one.
1, 2, 3, 4, 5. So cosecant tan? I'm sorry, cosecant cotangent?
Yeah. Alright, is the derivative of negative cosecant?
Yeah.
Okay.
Right? We remember these formulas from before, right? We're just working the formula backwards now.
Oh.
Okay, so I'm just going to write that little piece right down here. So the integral of f of x dx. Ask yourself. Oh, I need to plug in. Ask yourself, what is f of x the derivative of? Sorry a minute, there you go. Should be able to see that now, I hope. Plug in my computer.
Extend the screen.
Shut up. Yeah, you think I'm technologically useless here. I bought an inexpensive Android phone. I was getting lost in all kinds of different ways. Okay. Did you extended the screen, didn't you?
Wait, did you finish
What?
that story?
No, I
You guys
didn't.
extend this to? Okay.
No, I wanted to extend the screen,
All
but
right,
you told
but-
me not to.
All right. A minute. All right, what does it say here?
So Minette, when the video's cut off at the bottom because McDee's going to the end of the paper and the recording doesn't, that's his fault.
Okay. So why is this? Oh, I know why. There we go. That's better. Okay. Great. So ask yourself, what is this the derivative of? So Minette, hopefully you have already copied these formulas into your notes. I know that all of the people here have done that. Good. So, great. Okay. So let's actually do a couple of these and make sure we can use the formulas, and then we'll move on. So let's do the integral. So I'm just going to ask you to integrate. Where are we here? Integrate. So the integral, the big S means integrate. The integral of the sine of 7x dx. Please take a moment to integrate using your nice new formulas that you have. Sine of 7x dx. Are we all done? Okay. So again, just, intuitively asking yourself, what is the sine the derivative of? Sine is the derivative of negative cosine. Right?
Got negative sign from way off, but yeah.
Okay, good. So,
Yeah, why is it negative?
Because cosine's negative sign, but you have positive sign, so I have to get the negative.
so let's just
Gotcha.
remember from before, so d dx of sine of x we know to be
Cosine.
cosine x. We know this. And from before, d dx of cosine of x equals
Negative sine.
negative sine x. If we said, what's the derivative of negative cosine of x?
Sine x.
That would be sine of x. Right? We just transferred the negative sign from here to here.
But does that mean the sine of x derivative? No. Oh, jeez. Never mind.
These are both positive, so we don't need to worry about changing signs.
Yeah.
It does.
What's scary is that it's the derivative of one thing, it's not the derivative of another.
Give me an example of that.
So like I was saying, the derivative of negative cosine x is sine x.
Yep.
That doesn't mean that the derivative of sine x is negative cosine x.
Correct. Yes, you're right.
Don't like that.
Sorry.
It's scary.
It's okay.
Okay.
That's why integrals are more challenging.
Yeah.
Okay. So, are we good in saying now that the integral of sine is really negative cosine?
Yes.
Because of this little relationship that we just saw right here? So we have negative cosine of 7x over 7 plus c. Don't forget the plus c.
CCC.
Okay, are we good? All right. So another example for you. Let's do the integral of secant squared of 4x dx. Please take a moment to integrate secant squared of 4x. Good?
Mm-hmm.
Okay, what did we get?
Tan 4x over 4.
Tangent of 4x over 4
Plus
plus
c.
c. Are we all good? Okay.
That's when it's gone.
Yes, there's no doubt. It's definitely going to be more challenging. We already talked last time about integrating expressions with several parts. For example, the integral of 5x squared plus 3x minus 2 dx. How do we integrate something that has a whole bunch of parts? Something we talked about last time.
You just do the integral for each part.
Yeah, we just integrate each part separately. We don't need to try to think about this as one big complete unit here and ask ourselves, well, what is that the derivative of? We can just think of it as several different pieces, several smaller pieces. So this is really the same as the integral of 5x squared dx plus the integral of 3x dx minus the integral of 2 dx. Right, I'm just writing out three different integrals, one for each part of the expression. Just the same thing as we did when we had derivatives. When we have the derivative of a multi-part expression, we just take the derivative of each part separately. Okay, so same thing again applies to integrals as we did with derivatives. When we had a constant multiplier, what did we do with it? Just kicked it out, just kind of ignored it for a little while and then did our business. So I'm really going to say that this is the same as 5 times the integral of x squared dx. I'm going to take the 3 and throw that on the outside as well, plus 3 integral of x dx, and minus, I'm just going to leave the 2 there because this one's going to be easy to think of it just as it is. Okay, so from last week, when we integrate x squared, what do we have to do?
You have to add 1 to the exponent and divide it by n plus 1.
Right, so add 1 to the exponent and divide by the new exponent. So in this case, we're going to have 5, just bringing the 5 down, times x cubed over 3 plus 3 times x squared over 2 minus, what is 2 the derivative of?
2x.
2x. And of course, as always, stick on a plus c at the end. And then we can clean this up a little bit by writing 5/3 x cubed plus 3/2 x squared minus 2x plus c. But I don't have room on my paper, so I'm just going to leave it like that. We're all good on this? Great. Here is a mixed problem for you. I'm going to give you some trig and some polynomial stuff for you to integrate. So we're integrating the various little pieces here. So let's do 7x squared minus the cosine of 9x dx. Please take un momento, por favor, to integrate 7x squared minus cosine of 9x.
We're done.
Good. All right, so what did we end up getting? Thanks, I'm just looking ahead of here a little bit. So what did we get?
7/3 x cubed minus sine 7x over 7 plus c. Is it, wait, is it not cosine?
That's a 9, whatever.
Oh,
Yeah,
sine.
so that's fine. So,
Yeah, just 9. Minus sine 9x over
sine of 9x over
Plus
9
c.
plus c. Did we all get that correct?
Mm-hmm.
So, show your hand if you got it correct. Okay, good. Great. Questions? Anyone? Bueller? All right, great. So we've done some polynomial expressions with whole number exponents, and we've done some trig stuff. Let's throw in a fractional exponent.
Pain.
Let's throw in some pain, exactly. So let's do 9x to the, I don't know, 2/3 power dx. So this is really no different than the other stuff we've already done. It's just got a fraction in it, so we're just going to have to add 1 to the fraction. No big deal. And we can just function just fine. So again, I'd kick out the 9 so we don't have to worry about it. X to the 2/3. I'll try to write a little bigger, Minette. X to the 2/3 dx. Okay, so as we look at x to the 2/3, we need to add 1 to the exponent. So adding 1 to 2/3, we get 5/3. So we're going to have 9 times x to the 5/3 over 5/3 plus c. So what do we do when we divide by 5/3?
Multiply by reciprocal.
Multiply by the reciprocal, so we're going to multiply by 3/5. So we're going to have 27 over 5, 27/5 x to the 5/3 plus c. All done. Are we feeling kind of groovy?
Seems like a horrendous answer.
So, wait. Isn't that bad? You just wait. All right. Doing okay?
Yeah.
All right. I don't know where the microphone is here, Minette, so I'm hoping you're hearing everything. Were you able to hear everything?
Mm-hmm.
Okay, good.
Yeah.
Maybe it's right there. Okay. So we took care of that. Okay. So let's do another integral. Again, these are all things that still are using the power rule, because that's the only thing we have. We have the power rule and we have trig stuff. And the power rule, again, is just increase the exponent by 1, increase the exponent by 1, and divide by the new exponent. So let's take a look at a problem such as 3 minus 2x squared dx.
Wait, sorry. Oh.
Okay, so as we look at this, we don't have any rules right now. Actually, let me back up just a little bit. If we looked at this expression right here, and we said, hey, let's take the derivative of this, we would likely use what method of differentiation?
Chain rule?
Chain rule. And right now we don't have a reverse chain rule. We're going to come back to that later, not today. So we don't have a method for that. So if we didn't have the chain rule, as we looked at this, what would we do instead?
Write it out as 2.
Write it out as two things and multiply it out and then take the derivative of each of those pieces. We're going to do the same thing here. We're just going to square it out first and then integrate the little pieces. So whenever you can change something into a format that is better for you, go ahead and do it. So in this case, squaring that out is going to be a lot better than trying to do any other method. So just square that thing out and integrate the little pieces. So I just squared it out, and we got 9 minus 12x squared plus 4x to the 4th dx. And then we integrate all those little pieces, and we should get 9x minus 12x cubed over 3 plus 4x to the 5th over 5 plus c. And of course 12 thirds makes 4, so 9x minus 4x cubed plus 4x to the 5th over 5 plus c. Or if we were really cool, we'd put it in ascending order, or descending order, I mean. So 4/5 x to the 5th minus 4x to the 3rd plus 9x plus c. All done. It's good? Okay. Brilliant. All right, that takes care of that. Actually, let's do one more that involves trig, and then we'll call it a day on that. Okay, so let's do one more, and let's integrate sine of 4x minus cosine of 2x dx. Please take un momento, por favor. Sine of 4x minus cosine of 2x dx. Okay, are we done? All right, what did we get for the integral of sine of 4x?
Negative cosine 4x over 4.
Negative cosine of 4x over 4. How about, we'll just put a minus sign here. What's the integral of cosine of 2x?
Sine 2x over 2.
Sine of 2x over 2 plus c, and we're all done. How many got that correct? Yay! Okay, we're good? All right, nice. What's this crap? Good, interesting. All right, let's get rid of that. On to the next page. Okay, so far we've just integrated in very general terms, and we have left things in terms of plus c. But as you recall from a previous lesson, if we do the derivative of, so let's do a little exploration here, so we're going to explore. So if we do the derivative of 3x squared plus 2, and we do the derivative of 3x squared plus 5, we see that the derivative of both of these is, come on, come back into focus. There we go. We see that the derivative of both of these is
6x.
6x. Both times, 6x. So the problem, of course, arises if we tried to integrate 6x, would we get 3x squared plus 2? Or would we get 3x squared plus 5? Or would we get something else? So actually what would end up happening is we just integrate 6x, and so let's just explore what that continues to look like. So we're going to integrate now. Integrate 6x. So we do the integral of 6x. What do I write after the 6x when I'm integrating?
dx.
Dx, good. Making sure we're still working with x here. And how do we integrate 6x to the first?
Add 1 to exponent, divide by new exponent.
Good. So now we have 6x squared over 2 plus c. And 6 over 2 is 3x squared plus c. Which again is the same stuff as we got up here. It's 3x squared plus 2, 3x squared plus 5. How are we going to find out what c is? Well, we have a method. And the method for finding out what c is to get some additional information. So, to find c, it is necessary, write this down, it is necessary to have additional info, often in the form of an initial condition. In other words, when x equals 0 or t equals 0 or whatever the problem requires. So to find c, and we can if we're given some additional information. Are we good? So right now we're just going to find a specific integral. So far we've done general plus c, so now we're going to find a specific. Sorry this isn't as entertaining as the usual show is, but it's a little harder to entertain while I'm chained to this little desk here. Find a specific integral, and we're going to do the integral, the integral of, let's do 3x dx, and f of 2 equals 9. Okay, so what this means for us, we're going to try to find c, but before we even find c, we have to integrate. So we integrate here, and so we're going to get 3x squared over 2 plus c. All agreed? Okay, great. So now we know that we can say that f of x equals 3x squared plus 2 over c. And we know that f of 2 is equal to 9. So we put in 2 for x. Where's the 9 go?
Y.
That's where the y is, and the y, of course, is the same as f of x. So we write 9 equals 3 times 2 squared over 2 plus c. So the 2 goes in where the x was, and the 9 goes in where the y was. And then we just solve. So 2 squared, of course, is 4. So we have 9 equals 12 over 2 plus c. 9 equals 6 plus c. C must equal 3. So then our final and complete specific answer is f of x equals 3 halves x squared plus 3.
How would you know if you're integrating the first derivative or the second derivative?
Oftentimes these problems are set up as velocity and acceleration problems. So we'll be told, for example, that we have the acceleration. So I'm not going to do one of those problems right now because that's a little further than we need to go right now. But so we would integrate the acceleration to get the velocity. Then we'd integrate the velocity to get the position. And so in each step of the way, so we'd be given an initial condition for the velocity, so we could fill in the c for velocity. Then we'd know what to integrate for the velocity so that we can get the position function. And then we'd have a specific information for the position function. Does that make sense? Okay. Actually, you know, it's not that hard. Let's do one of those. Okay. So here's an example. So
Spencer's dying.
Sarah's not happy, but that's just too bad. All right. So let's say that a of t equals, I don't know, 4t. And we know that v of 0 equals 6. And we know that s of 0, remember s is position for reasons that are unclear to everyone in the world, s of 0 is negative 2. So we're 2 feet behind the starting line.
Okay.
All right, so we want to find, oh, so I didn't ask you what's going on here, find the specific position function. So what are we going to do in order to make that happen? Do we all, I guess I may have jumped ahead here, I think we've already done it, but do we all know that the first derivative of position is velocity?
Second is acceleration.
Second is acceleration. Great. Okay. So remembering that derivatives and integrals are opposites of each other. So how do we move from acceleration towards position?
Acceleration towards position?
Yeah.
Find the integral of acceleration.
Acceleration, then integrate that again, because that'll be velocity, then we integrate the velocity to the other position. Okay. So here it is. So we're going to integrate 4t dt. Which is 4t squared over 2 plus c and what's 4t squared over 2? 2t squared plus c. And so we've just integrated acceleration, which is 4t. And when you integrate acceleration, what do you end up with? Not position.
Velocity.
You end up with velocity. So v of t equals 2t squared plus c. But we know something very specific here. We know that v of 0 is 6. So just like in the previous problem, we plug in 0 for t and 6 for v in this case, but yeah, y, v, same in this case. So we write 6 equals 2 times 0 squared plus c. Of course, 2 times 0 squared, that goes away, so 6 equals c. So now we're prepared to write our specific what function?
Position function.
Not yet position. We can write our specific velocity function right now, right? We can write,
plug it back in.
yep, so v of t equals what?
2t squared plus 6.
2t squared plus 6, because we just found out that c was 6, so we're going to put that right there. So that's our velocity function. So if we want to go from velocity to position, we have to integrate. So we're going to integrate 2t squared plus 6. So we're going to go from velocity to position. So I'm going to write you a note here. Integrate velocity to get position. So we can say S of t then equals the integral of v of t. Does that make sense? S of t, this is a position function, and that's going to be equal to the integral of the velocity function. Right, just working backwards. The derivative of position is velocity. The integral of velocity is position. They just go backwards. Okay, so S of t equals the integral of 2t squared plus 6 dt. Still working with t. So, integrating that, we get
2/3 t cubed plus 6t plus c.
Are we all in agreement? Great. And we know that S of 0 was negative 2. Is that what I said? Negative 2. So we're going to plug in 0 for t, negative 2 for S, and we're going to find c, which, no surprise to anyone, is going to end up being negative 2. So S of t equals 2/3 t cubed plus 6t minus 2. There's our specific position function. Does that make sense to y'all? Little Sarah, how are you doing?
Mm-hmm.
All right.
Good.
You want to do this with a trig function?
No.
Good. All right, so here's the question then. Find f of x if f prime of x equals sine x minus cosine x and f of pi equals 3. So we want to find f of x, and we were given the derivative. So how do we go from the derivative to the original function?
Integrate.
We integrate. If you integrate the derivative of something, you'll end up with the original function. All right, so I'm going to write that as a general rule. F of x equals the integral of f prime of x. That's just a general rule. If you integrate the derivative, you get the original function. Okay, so we're going to integrate. Actually, do you want to just do this on your own? Good.
I have a question.
Yes.
So you have sine x, right? Since it has to know, well, the a is 1, right, for sine x?
Yes.
Okay.
Yep. So use your little formulas, or think of it intuitively. What is this? So as you're looking at the integral, what is this the derivative of?
Pi is 1/180.
None of the above. 180. Remember, visualize those graphs.
That's the easiest way for me.
Visualize the graph?
I used to like try to think of
Yeah, try to memorize
a
it.
table I saw. which
Oh,
was
yeah,
like
yeah, there you go.
sine.
Yeah.
That's hard. But
Yeah, absolutely.
It's easier.
Picture's worth 1,000 numbers, or something like that.
I'm good, I'm just rewriting it.
Mm-hmm. Okay, so what did we end up with?
Negative cosine x minus sine x plus 2.
Negative cosine x plus sine x
No, minus sine x.
minus sine x plus 2?
Yes.
Okay. Did we all three get that? Good. We feel okay about it? All right, Minette, hopefully you got the same thing. Okay, great. Questions so far on integrating and finding a specific function, which we just did a couple times? Okay, great. All right, we're moving along quite well here. I'm trying to decide, I've been trying to decide for the last few minutes here, what direction we want to go with this. I'm just going to go in the order that they have right here in the book, in your review book, so that we can just keep going straight and not have to worry about backtracking or forgetting that we skipped over something or what have you. So we're going to enter into a part of it, or a method of integration that is a little challenging, a little hard to get your head around sometimes, but if we just go with the procedure, we should be able to keep ourselves fairly straight and not get too lost. So again, I want to start back with the question, what is this the derivative of? So let's do a little exploration here. And we want to integrate 3x plus 1 to the 5th dx. Okay, so let's just think about this in terms of, again, the question. What is this the derivative of? And we don't know yet, but we can make some sort of approximations about what it might be the derivative of. So, what is your guess that this might be the derivative of?
3x plus 1 to 6 over 6.
Right, does that make sense?
Yeah.
Okay, because we're just going to increase by 1 and divide by the new exponent, or the new exponent, right? Okay, so let's just try that one. So we're still exploring here, and Jeremy has made a suggestion that maybe the integral of this is equal to 3x plus 1 to the 6th over 6. So if that's... Right, plus c. Thanks. So if that's true, then the derivative of this must be that. Would we agree? Okay, so if this is really the answer to this integral, then working backwards, if we do the derivative of this, we should get that. Okay? Well, then let's find out. So, find, derive, and compare to integral. So let's do the derivative then of d dx of 3x plus 1 to the 6th over 6 plus c. So how do we do the derivative of this?
Chain rule.
We do the chain rule. So we bring down the 6 in front. So it's 6 times 3x plus 1 to the 5th, still over 6 here, right? Times
D inside.
the derivative of the inside, which is 3. And then we have plus c, but the derivative of a constant is 0, so we don't need to worry about that. We don't write plus 0 or anything. These 6's cancel off, right? And we have 3 times 3x plus 1 to the 5th.
What about C?
We did the derivative of c,
Oh.
which is 0. right? So plus 0, right? Derivative of c is plus 0, so we don't write that. Okay? So let's compare. Let's compare this to this. Are they the same?
Yeah.
They're close to the same, but they're not exactly the same. What's different?
One's 3 times bigger than the other one.
Okay, so basically what we can say is that there's a 3 down here that isn't up here. And where'd that 3 come from?
The derivative of the inside.
The derivative of the inside, right?
So it ignored chain rule.
So it ignored the chain rule, right? Because actually that's what we're doing right now. We're actually working the chain rule backwards. U substitution is what we're going to be working with in just a minute. This is essentially working the chain rule backwards. So what we can say then is that this isn't the derivative of anything that we're aware of, because we're missing a 3. If there was a 3 here, then we could say that this was the derivative of that.
Yeah.
Does that make sense?
Yeah.
Right? We showed that we did the derivative of this, we got something with a 3. So therefore, if we integrate this, we should get the same thing, but we don't. There's a 3 missing. And the 3 comes from this. So the question is, how do we go about fixing this?
You divide by the derivative of the inside.
Yes, we are going to do that.
Yeah.
So here's the way we're going to go about fixing this. And this is the intuitive method. I'm going to show you the intuitive method first, and then I'm going to do the specific U substitution method, which is going to be very helpful because it's going to help us to keep things organized. Okay? So, and this is an important point here, and I need to know from you, all of you, right now, that you understand beyond any shadow of a doubt and any confusion that there's a 3 missing here. And that 3 came from the inside here. And if we wanted to integrate this, to get this, we need that 3. Everyone's got that nailed down and they understand completely why that's the case. Okay, great. So we can't integrate this as it is because this isn't the derivative of anything yet. We'll only be able to integrate this if there is a 3 right there. There has to be a 3 right there. Everyone's cool? Okay. So this is not, it actually is, but I'm just making a dramatic point here. This is not the derivative of anything. It really is, but I'm trying to make a point here. This is not the derivative of anything. It is missing a 3. Right? And we've just had this discussion about why the 3 is missing. Okay. So we can't just go around in math throwing 3s wherever we want them. Right? Because that's not cool. We can't just multiply by 3.
So great.
That would be great. Oh, damn, I missed it by 3. Oh, we'll just put a 3 over here and it's all set now. So we can't do that. But what we can do is we can multiply anything by...
So,
No.
okay.
What can we multiply by and not really affect anything? Multiply by 1. Does that make sense?
Yeah.
Okay, so here's what we're going to do. We're going to rewrite this problem.
Yeah, I need some tissues.
Okay, go get some. I'll pause.
No, tissue.
I am taking my time. If you need tissues, you go ahead and get some tissues right now.
No, math's more important.
All right, that's what math is more. That math is more important. Okay, good. All right, so we've all agreed that we need a 3. We need a 1. We need a 3, but we can't just throw a 3. We need a 1. So here's the way we're going to fix this. So we are going to rewrite this integral as 3x plus 1 to the 5th times 3 dx.
If I thought you just can't add a 3 anyway.
I'm gonna fix that, and you just keep watching. My show's not over here.
I think you spoke to me.
Okay, so we did multiply by 3,
Yes.
but that's illegal.
It is illegal.
We can't multiply by 3.
No.
So what I'm going to suggest is that in addition to multiplying by 3,
Divide by 3.
we are also going to divide by 3 or multiply by 1/3. So I'm going to put in here also
I don't like this.
times 1/3.
Okay.
But this makes no sense. Why would you do that?
Because what's 3 times 1/3?
1.
1. And what's 1 times anything?
Legal.
Legal. It's itself, right? I haven't changed anything. If I multiply by 1, I haven't changed anything.
You're so,
Yeah, but then what's
you're
the
such a
point of
cheater.
multiplying by 3 and 1/3?
You're going to see.
I don't like it.
You're such a cheater, McD.
Okay, is everyone good so far? Have we done everything that's legal so far?
Yeah.
Multiply by 3 and by 1/3, right? Okay. Now, we all know, because we've talked about it before, that anytime we have any constant multiplier, we can kick it on the outside and then carry on our business.
Go ahead.
But then it is
Okay.
illegal.
Just do it.
You just watch what I'm doing here. I have 2 constant multipliers here.
So we can only give it one.
I'm going to pick the one I want to put on the outside. Which one do you think I want to put on the outside?
Probably the 1/3.
I want to put on the 1/3 because I want to leave in the
3.
because I need it. We're all good on this?
My God.
So I'm kicking out the 1/3. Then we have,
Who came up with this?
Guy on acid.
I don't know. Okay, so now I've been able to, I've been able to rewrite my integral in a way that this is now the derivative of something. Is everyone okay?
Yeah.
All right. Because we said before that we needed a 3, we put in a 3. But like I said just a moment ago, we can't just go put in 3s where we want them, but we can multiply by 1. So multiplying by 3 and multiplying by 1/3 makes it all good.
So now
Are
we
you
can
sure you
take
put
the
in the
derivative.
3 the right way?
I'm sorry?
Are you sure you put in the 3 the right way?
I did?
Because wouldn't you get like 3x instead?
Shouldn't it be 1/3 and then the 3?
Well, so let's look right here. Do we all agree that this is the derivative of that?
Yeah.
Yes.
Does this look like that?
Yes.
Okay. So we made this look like what we wanted it to look like, which is this,
And now if you
which is
use
the same as
1/3,
that, right?
You just took what you
Oh
wanted.
wait, no, I'm silly. Yeah, okay. Yeah. Because you're
Right.
you're integrating that, and that's right derivative. Yeah, okay.
Okay?
Yeah, no, okay, I get you.
Are we good?
Yeah.
Okay. So now, when we integrate, so we did the derivative of this, and went this way and got this answer.
Mm.
And that's the integral.
If we integrate this, what do we end up with? That. Right? Remember, they're just opposites of each other. The derivative of this is here. The integral of this is there.
Yeah.
Are we good?
Yeah.
Okay. So now we can integrate this, and we're remembering really this is just the backwards chain rule. The chain rule requires that we have a function, an inner function like to a power, times the derivative of that function. That's the chain rule. If we don't have the derivative of the function, then we didn't do the chain rule right. Okay? So now we can work backwards. What's this the derivative of? That. We're all in agreement? Great. Okay. So, we
The
now
original
have,
thing is just a piece of crap.
which original thing is that? The 3x plus 1 to the 5th? Okay. It's sort of a piece of crap. So again, I want to remind you that this was Jeremy's best guess at what the integral of this was supposed to be.
Good.
Okay? And it was a reasonable guess. But what we recognized here is even this guess here is going to be a little incomplete because we're missing a 3.
Okay.
Okay?
So the integral of that was wrong, so we...
Yes, so again, this was his best
Yeah.
guess, and it was a mistake. This is not a correct integral of this.
Okay.
But it was a good guess, and it made complete sense. And we checked whether this was the correct integral of this by doing the derivative, and those two should match up if it is, and it wasn't. Okay? And so through this exploration here, we remembered, oh yeah, we needed to have a 3 here. So we need to have a 3 here if we're going to integrate this. And we can't just throw 3's around. We need to put in a 1/3 to balance off the 3. Are we good? Okay, so now here's the big question. We're bring down the 1/3. What is this the derivative of?
Exactly what we want it to be.
What is that the derivative of?
3x minus 6 thing.
Right? Are we good? And then we're just going to complete the answer now. 1/3 times this is just going to make 18 on the bottom now. Okay,
So what do we find? We found the derivative of.
we found the integral of this.
So we
By
proved
doing the integral and then the derivative of the integral.
Sort of. And we only did this piece over here just to explore and discover the idea that if we're really going to integrate this properly, we need to make sure, essentially we're doing the chain rule backwards, that we have the derivative of the inside. That's what we discovered by doing this little exploration over here. So now, once we've discovered that, we don't have to keep doing this over and over again. We've discovered this piece of information. So now we know whenever we try to integrate something that looks complicated and is not going to allow us to use just the power rule that we have already, we need to use something more powerful. We need to recognize that if we have a complex function, we need to have its derivative alongside. That's the only way we're going to be able to integrate this.
So if you had 4x plus 1 to the 5th,
Mm-hmm.
it would just be 1/4 integral 4x plus 1 to the 5th times 4.
Correct.
Okay.
And we can even get better. So I'm gonna go a little more advanced here. I'm not gonna actually have us integrate this, but I'm gonna have you tell me what's missing. So here's the question: what's missing from the integral? So let's do 7x squared plus 3 to the 19th dx. And I don't want you to integrate this. I just want you to tell me what's missing from this integral.
14x.
14x. It's really simple to figure out what's missing. All you got to do is do the derivative of the inside. So 14x is what's missing. We would like it if there was a 14x right there, but there isn't.
What do you mean what's missing from the integral?
Remember from the previous page?
Is that to the 19th?
Yes, it is.
Oh, okay.
Okay, doesn't really matter, right? It's just a number.
Yeah, it's just big.
Right, remember from the previous page, what we found here, what was missing was the 3 that's down here,
Yeah.
but the 3 was just the derivative of the inside piece.
But it doesn't sound right just to say what's missing. I mean, like,
It's what you would need in order for the integral to work.
yeah.
Yes.
What's missing to make it a real derivative?
An integral that we could work with.
Yeah, okay.
Yes.
What's missing in order to get back to the derivative,
Yeah.
which is
Yeah.
basically the integral.
Are we good? Okay. Let's keep going. Let's do the integral of sine of 7x squared. Oh, why did I do 7x squared again? Okay, fine. I'll do 7x cubed minus 2x dx. I want to know what's missing. The answer is 21x squared minus 2. That's what's missing. That's what we would like to see right there. Are we cool? All right. So, I'm going to go one step further with this example right here, and then I'm going to begin to show you U substitution. Because as these problems get more and more complicated, it becomes a little less clear what's missing.
I understand what to do, but I don't understand what it gives us.
What it gives us is, and you explained it well to Spencer.
Okay, so you start with it. This here is, what is that?
So,
Is that an integral or derivative?
so this is, well, again, just remembering the integrals are the opposites of derivatives. This
Mm-hmm.
is the derivative of something,
Okay.
or it's part of the derivative of something,
It's a false shepherd.
and it's missing something.
Uh,
It's missing 14x. If it had
Yeah.
14x, it would be the derivative of something that's very clear and easy for us to get to.
okay.
And that's what we're trying to do. How can we set up something that's clear and easy for us to get to? Okay? So again, these actually aren't so difficult, right? You just looked at this and said, oh, 14x is what's missing. That's obvious. But it's not going to be so obvious. It's going to get fairly complicated. And so we need to have a method for us to be able to find our way through the complications. And that method's called U substitution.
Okay.
Okay? So I'm just going to show you one step beyond this, and then we're going to do U substitution. We're going to actually do one of these problems with U substitution. Okay. So let's re-explore this one here. We're exploring again. We're exploring the integral of 7x squared plus 3 to the 19th power times 2x dx. Okay.
Times 2x.
Yep, times 2x.
Okay.
All right. So now, so this isn't quite good, right? But it's closer to being good than this was.
Yeah.
This was missing a whole bunch of stuff.
I'm missing a 7.
Okay? So Sarah says, hey, I know that because the derivative of this thing here is 14x.
Oh, it's like kicking out the 7.
That's right.
Okay.
I know that I'm supposed to have right here a 14x. But I don't. I have a 2x. So, how do I make a 2x into a 14x? Multiply it by 7. So I'm going to multiply by 7 here, which means I have to multiply by 1/7 out there. Does that make sense? Okay. So the question you're asking yourself is, how can I make 2x into 14x? The answer is multiply by 7. So I'm going to rewrite this problem here as the integral of 7x squared plus 3 to the 19th power times 2x times 7 dx. That's right. But again, if I'm just going to multiply by 7 here, that's not okay. That's not 1. If I'm going to multiply by 7 on the inside, I got to multiply by 1/7 on the outside. Are we good? So now we can say that this is 1/7 times the integral of 7x squared plus 3 to the 19th times 14x dx. This is now the derivative of what? What's that the derivative of?
Yeah, the original.
7x squared plus 3 to 20.
20. Yeah. Plus
Right?
14x squared over.
No, this is times.
Oh,
Right?
is it,
So what is this the derivative of? This is a chain rule problem, right?
yes.
Right? Right, because there's the derivative of the inside. It's right there, 14x. So this is the derivative of, just this piece right here, I'm going to write over here. That's the derivative of 7x squared plus 3 to the 20th over 20 plus c. We all agree?
C.
But we need to multiply by 1/7 because we can't just leave the 1/7 off.
So the 14x doesn't even matter.
It does. This is the derivative of the inside. When we do the chain rule, we have to include the derivative of the inside right there, right after it, right?
Yeah.
So we're working the chain rule backwards. So the answer to this is really 7x squared plus 3 to the 20th over 140 plus c. That's our answer. Are we good? Okay. Since we've been exploring this one, I was going to start with an easier one, but we've had a lot of exploration with this problem right here. We've already worked it twice. looked at it twice. I'm going to continue to explore this problem, and I'm going to use this as our basis to learn U substitution.
think that'll take up a lot of room.
Um,
Go new page.
yeah, you're going to need it. Yeah, you might be able to do it in there, maybe. Okay, so we're going to start with this problem right here. We're going to explore U substitution. And we're going to explore it by looking at this problem right here. A little more challenging than I usually do, but
Why
since
don't we do one easier? That'd be nice.
Let's
well, we're already here. Shut up. Okay. I'm hoping this is going to be okay to skip ahead a little bit. Okay. So, we're trying to make this problem as easy as possible for us to work with. So, it makes sense to call the inner function something easy to work with, and we're going to call it U.
because you're easy.
Because you're easy.
Getting
Something like that, yeah. Okay. So we're going to write that right over here. We're going to say that U is 7x squared plus 3. And we're going to need this. Du dx, the derivative of the inside, which of course we know we need because we've just talked about it a lot, is how much? 14x. So we're going to need to do some substitutions here, because that's what we're doing. We're doing U substitution. So now we're just going to rewrite this integral, making substitutions. Actually, I want to go one step further here. I want to solve this piece right here for dx, because we're going to have to sub away dx, so I want to make sure that we're solved for dx here. So solving for dx just means to flip the 14x and the dx,
Okay.
right? So we
So
get,
dx is like a real thing.
it is a real thing,
Guys always just kind of hiding
right? So dx equals du over 14x. Are we okay?
there. I guess, but that seems scary.
All right. I agree with this is scary. So I am going to actually backtrack. This is going to be too, so just, it's okay. So
Freaking told you.
you're going to be okay. It's going to be fine. So we are going to work this one with a little easier problem. So let's integrate instead 3x plus 1 to the 5th dx. So, just so that we know what's going on here, what are we missing again?
3.
We're missing a 3, and therefore we're going to put a 1/3 on the outside, right?
Mm-hmm.
Okay, cool. All right, so we are still going to do what we were doing just up there just a moment ago. So U, in this case, is
3x plus 1.
3x plus 1.
Du
So U equals 3x plus 1, and du dx
3.
equals just 3.
Do we have to do dx?
So what
Yes.
is dx then, if it's an actual thing?
Remember
They're different than dx.
Remember back last week, we were doing the linearization thing, and we talked about the dx was just that little bit of space along the x-axis.
A little bit of change.
Yeah, it's just a little bit of change. That's what dx is. In a couple of class periods where I'm going to be able to give you a visual that you'll be able to understand what dx is in terms of integrals. But right now,
Just accept it.
just accept it. But I will give you a visual so you're like, oh, I see what dx is all about now.
It's the point one of that.
Yeah. Okay, so we're going to flip the 3 and the dx. So dx equals du over 3.
Okay. So you really can't write u prime, or that really screws stuff up.
Yeah, that's not going to be helpful here because of the format. Okay? So now we're just going to substitute all the things we can. So in place of 3x plus 1, I'm going to write
Should you do the 1/3 thing on the outside?
Nope. Nope.
That's no.
That's the beauty of this. This whole process here, if you just follow the process exactly the way I show it to you, this will take care of the 1/3 for you. You don't have to think.
I'm good at that.
All right, there you go. So instead of 3x plus 1, we're going to put in u, because that's what it is.
U to the fifth.
And this is u to the 5th. We don't even need parentheses anymore. Right?
That's so easy.
I know. dx, we've already solved for. That's the same as du over 3. That's the same as du over 3. But du over 3 is really just the same as 1/3 of du.
Sure. Yeah.
Right? Divide by 3, same as multiplying by 1/3. Right? So that's the same as the integral of u to the 5th times 1/3 du. Is that good? Great. Now, we see the constant multiplier 1/3. We can kick that to the outside. So now we have 1/3 of the integral of u to the 5th du. Integrating u to the 5th is easy. How do you integrate anything to the 5th power?
Add 1 to exponent and divide by the exponent.
That's it. Right? Okay. So, we have 1/3 u to the 6th over 6 plus c. Agreed?
Why would you do du?
What do you mean? Remember,
Yeah.
remember, this just says this is what to integrate with. We're integrating with u,
Oh, using u. Oh.
right?
Yeah.
Again.
It's weird that you can use it and then it's no longer a thing.
Right.
That's
Well,
pretty creepy.
and you'll see why it isn't a thing later, but right now we can't. It'll be confusing to talk about it now. So 1/3 of u to the 6th over 6 is going to be u to the 6th over 18 plus c.
Which is the same as
But u, of course, is just
here.
3x plus 1. So we just back substitute at the end and we're done. 3x plus 1 to the 6th over 18 plus c.
Why would that have been hard with the other one?
It wouldn't be difficult using kind of an intuitive method. Hey, we're missing a 3, therefore we put a 1/3 on the outside, da 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 da. We would have been fine. It gets, trust me, it gets way more complicated than we just need a 3.
What I was saying was like, why was it so much harder?
You're going to see. Okay, so now let's continue this problem in the same fashion we just did here. Okay, so we'll move along kind of quickly as we go through this problem.
Oh, that's a good idea.
Yeah. So, in place of 7x squared plus 3, we're going to put in
U.
u. So we have u to the 19th
Times 2x.
times 2x. We're going to leave the 2x there, and you're going to see what happens to it in just a minute. You can guess what's going to happen, right?
It's not good.
Okay, and dx is
14x.
du over 14x.
Oh, oops.
du over 14x. Good? Okay, so we're remembering, what did we need here from before?
2x.
This was supposed to be 14x, but it's 2x, so we needed a 7. Right? And so we're going to have a 1/7 on the outside. That's what we should have if we do this right. Okay. So notice the 2x and the 14x, they're going to cancel off, and we're going to be left with 1/7.
Oh.
So equals u to the 19th times 1/7 du. Where does the 1/7 go?
Outside.
1/7 integral u to the 19th du equals
1/7
1/7 u to the 20th over 20 plus c. Equals u to the 20th over 140 plus c.
Which equals?
But u, from all the way back here, is 7x squared plus 3.
This is even better than u substitution for.
Yeah. So we get 7x squared plus 3. For recording, please and thank you. So 7x squared plus 3 to the 20th over 140 plus c. U substitution. Okay? This is a really powerful tool. This is going to get you out of a lot of stuff when we get stuck. Okay? All right, so let's make a little assignment here. And that assignment is going to be,
Guys, close the door.
so we're going to do set 20. Oh, sorry. Minute, I have all these notes here. They're all written down. So we're going to have an assignment here, and it's going to be set 20. Let's do, I think we can do all those. 1 to 15. And then we'll just do a few of the u substitution problems. And let's just do, oh my god. All right, that is all she wrote on u substitution. I'll give you 2 to try, but I think they're a little on the challenging side. I'm going to have you do set 21. Well, I'm telling you, we just started u substitution. Set 21, let's do 2 and 3. 2, comma 3. These are not easy.
Great.
They're not.
I love it when you start off something.
At least it's not 4.
All right, there you go.
Because we're doing 2 and 3. Let's
Okay.
4 is even harder.
Are we good?
Yeah.
All right, great. Thanks, great work. Thanks for hanging in there. Tell me this is stop.